All right, students, we're going to begin today by learning how to use a new function on our calculator. The new function is going to allow us to do some new math that you may not be very familiar with. One of these functions is we say e to the x, and the other function is we say ln, or natural log. And it turns out that both of these functions are usually on your calculator on the same button. So you see the button here, it says ln, that's natural log, and right above it as a second function is e to the x. Now, why are they sharing a button, and why am I putting them on the whiteboard at the same time? Because these functions are really related to one another. They're kind of like mirror images of one another. And to help you kind of understand how they mirror each other, it's helpful if we play around with the numbers. So when we say e to the x here, what we mean is that we're going to take a particular number called e for right now, and we're going to raise it to a certain power represented by x. So if x was 2, it would be e to the second power, or if x was 5, it would be e to the fifth power. Well, we're not ready to do the second or the fifth. We'll do some other things. Okay, and similarly, we're going to press the button for ln, and we're going to try to figure out some values there. So, ln. Why don't we start with 0? Because I already got a 0 here. I'm just going to press the key that says ln. And oh, look at that. If we take the natural log of 0, it doesn't mean anything. That's an error. So we won't be using that. What if we take 0 for e to the x? So the second function, e to the x. Well, that's interesting. If I go e to the x where x equals 0, then that's equal to 1. Well, that's not too terribly surprising, because you should know actually that any number raised to the 0 power becomes 1. But what happens though if I take the natural log of 1? So I've already got a 1 here. Let's press the natural log key. Oh, it's not an error, but it is 0. So I got a 0 here, and I got a 0 over there. E to the 0 is 1, and the natural log of 1 is 0. 0, 0, 1, 1. That's kind of like a mirror image. They're kind of reflecting each other. Well, I'm sure you can guess what's going to happen next. I'm going to do e to the 1, which of course is going to be just the same thing as the value for e. So let's take 1. Let's go second function, e to the x. Let's see what we get. Well, hello. 2.71828182828. This is one of those numbers that goes on and on, right? It's not rational. It can't be represented with a ratio of whole numbers. And it's said to be transcendent. It can just go on and on. Its expression could be infinite. Kind of like pi, right? With pi, we say 3.14, but we often mean a much longer strand. Then we press a button that says pi instead of entering 3.14. Well, this number e is one of those similar numbers that just goes on, and it's useful. And we'll figure out where this number comes from in a moment. For right now, though, the important thing is that if we take e to the 1, if we press 1 and we raise e to the power of 1, then it is approximately 2.718. Okay, now you may say, I don't see a mirror for that. But let's say we just take this number right here, and we're going to raise it. We're going to take the natural log of 2.718. Or actually, we're going to take the natural log just of e to the 1 power. Watch this. It's just 1. Or if we wrote it out, if we wrote out the approximation, the natural log of 2.718, we press that. Now here we don't get 1. You can see it's super close to 1. Why didn't we get 1? Because 2.718 is not the complete expression of e. The complete expression goes on forever. But if we just had that complete expression, and again, we can do that by going second function e to the 1. If we have that complete expression, and then we try to take the natural log of that, it turns it right back into 1. Okay, so e to the 0 is 1. The natural log of 1 is 0. That's a mirror. E to the 1 is 2.718, roughly. And the natural log of 2.718, e, is 1. So there are mirrors here. And the reason why they mirror each other, the reason why they share a button, is because they are actually two different ways to describe the same thing. They are two different ways to describe what's called an exponential function. The exponential function could be growing, in which case that's exponential growth. Or it could be decaying, in which case it's exponential decay. But we don't see straight lines with these functions. We see curves. And when we see curves, what that means is that every moment, the direction of the curve is changing. It's constantly changing. And so the usefulness of these functions, e to the x and natural log, the reason why they mirror each other because exponential decay and exponential growth mirror each other. And you can use them interchangeably, and you can go back and forth. And if you're not sure if you understand what I mean by that, well, again, let's take 1, right? That's just 1, all right? Natural, okay, we're going to go second function e to the x. There's that. Now we press that. And now we do this. And now we press that. You notice I'm pressing the same button. I'm just going back and forth between the function e to the x and natural log. And as long as I do that, the same relationship keeps happening over and over and over again. They really do mirror each other. So that's the relationship between e to the x and natural log, and that's why we're going to be using these buttons, and that's why I'm showing you how to use them, because we're going to use them for these exponential expressions, and that makes them very useful. Now what I want to do is I want to show you where e to the x comes from. You may say, well, why does this number, roughly 2.718, why does this number happen? Okay, so this time instead of saying e to the x, I'm just going to write the symbol e, and I'm going to tell you that the symbol e actually represents a sum of an indefinite number of mathematical operations. We actually get this number by doing a little math calculation, but we do it over and over again. How many times do we do it? As many times as we want. We could do it 10 times, we could do it 100 times, we could do it an infinite number of times. But this is the math operation we're going to do. And what it says here is that e equals 1 plus 1 over n raised to the n power. Now you may say, well, what is n? Well, n in this case is simply the number of times that we're going to do this calculation. Let's say that we just do it once. Let's say that we just do this once. We're going to do n equals 1. Okay. Well, if we do that, this becomes 1 plus 1 over 1 raised to the 1. Now, 1 over 1 is just 1, and 1 plus 1 is 2, and 2 raised to the first power, why, that would just be 2. Pretty straightforward. What if we, though, raise this to the second power? What if the n was 2? What if we do this twice? Well, that means we're going to multiply 1 plus 1 over n times 1 plus 1 over n. And so the n here becomes 2. This is 1/2. 1 plus 1/2. We're going to square that. And when we square it, we get this number, 2.25. Now we just keep going and see what happens. Let's do n3. One plus 1/3 to the third power. That's going to be 2.35. How about if n is 4? Well, that's going to be 1 plus 1/4 to the fourth power. We do the math. 2.44. And 5. What about 10? We'll skip a few, huh? Or 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 and so on and so forth. As we keep doing this operation over and over again, we keep getting closer and closer to this number E. We never quite get there, but we get very, very, very close. And so this is just a function that can go on indefinitely, and that's why we get this number. And when you do a function like this, at first, every time you change it, the number goes up quite a bit. But eventually you end up with a straight line, and the value doesn't appear to change. And so an operation like this, repeated over and over again, will yield the number E. And the number E, when used in operations, can be used to show an exponential growth process, because the process of constructing this number is an exponential process. It's this operation repeated indefinitely. We could even write it like this. We could say, instead of 10,000, we could use a symbol for infinity. 1 plus 1 divided by infinity to infinity power. Well, that will be precisely E. All right, students, so we've used the calculator and we figured out that we have two functions that are like mirror images of one another. Now, what I'm going to do is I'm going to show you a relationship which also gives us a mirror image. We are very interested in trying to measure how radioactive substances decay. We want to know how long they last. We want to know how fast they're falling apart. We want to know how much will be left after a certain time. That's what all these half-life problems are. Okay? So the half-life is one way of keeping track of the rate of radioactive decay. And another way is to use the actual decay constant. So this is the half-life. And this is the decay constant. Now these are both just two different ways of trying to keep track of the way that a radioactive isotope will fall apart. When we look at it from the point of view of the half-life, we're asking how much time is going to go by until about half of the substance is gone. Whereas when we're looking at the decay constant, we're saying right now, right at this moment, what is the rate at which this substance is decaying? how much is it falling apart right now? Two different concepts, but they're actually related. They're both just two different ways of trying to describe this phenomenon. Now, since one of the ways that we're doing this is to talk about the half-life, and the half-life is 1/2, we often use the natural log of 2. And what we do is we use the natural log of 2 to relate both of these concepts. At this point, we might ask ourselves, what is the natural log of 2? So we'll put 2 in our calculator, and I'll just press the natural log key. And what you're going to see is we get this number, 0.693147, blah, blah, blah. It goes on and on. But ordinarily, when we're doing these problems, we don't usually bother with all that. We just take the first 3 digits. It turns out that the natural log of 2 is approximately equal to 0.693. 0.693. Okay, well, it turns out that if I know either the half-life or the decay constant, I can use the natural log of 2 to figure out the thing I don't know. And again, this is like a mirror. So let's say that I know what the half-life is. I know what the half-life is. Check. Okay. Well, if I know the half-life, let's say that I know what the half-life is. Okay. So I'll just write T1/2 here. And T1/2 is going to be on the bottom because in the expression for e to the x, the way we get it is we are constantly having this changing fractional relationship, 1/1, 1/2, 1/3. We keep doing that. We keep adding that all up. We keep summing it. So we're going to put 1/2 on the bottom here. So let's say that we actually know the half-life of something. What we're going to do is we're going to put that half-life on the bottom of an expression. And on the top, we're going to put the natural log of 2. Well, the natural log of 2 is always going to be 0.693, or approximately 0.693. So let's just write it that way. If I know what the half-life is, and I just write 0.693, and that will be divided by the half-life, and guess what? That equals the decay constant, K. Or let's say that I know the decay constant. I don't know the half-life, but I know the decay constant. Well, that's natural log of 2 divided by K, which is the same thing as 0.693 divided by K. And guess what? That equals the half-life. Bottom line is if you know the half-life, T1/2, you can figure out K. If you know K, you can use that to figure out the half-life. Now I'm going to give a practical demonstration of that. Let's take cadmium-113. Okay, cadmium-113 doesn't have a very long half-life. Its half-life is 12.2 years. And so my question is, what is the decay constant for this isotope? If this particular isotope, cadmium-113, has a half-life of 12.2 years, what is K? Okay, well, we're just going to plug in natural log of 2, and we're going to divide that by the half-life, the thing that we know, 12.2. Now, natural log of 2 is actually 0.693. So we'll take that 0.693 and we will divide it by the half-life. 0.693 divided by 12.2. And when we do that, we get this number, 0.057. What's this number? Is there a unit with this number? Turns out the decay constant is unitless. It's just a number. But that's how you would find K. If you're given the half-life for a given isotope, 12.2 years, why, you can figure that out right here. All right. Let's imagine we can reverse this. Let's imagine that we have some element, and we'll call it X. And let's say that X is it's got a number of 71. We don't know what element this is. Doesn't really matter. But we're going to say that the half-life is unknown. But we've determined the decay constant. We're going to say that the decay constant is 0.00007. Okay? All right, so again, natural log of 2 divided by the thing that we know, which is K, which in this case is 0.00007. And this is actually 0.693 divided by 0.00007. So now we just do the math, 0.693 divided by 0.0007, and we determine, hey, it's 990 years. That's the half-life. It's that easy. So just as e to the x and natural log are mirror images of one another that are doing a exponential change, and we can turn one to the other, but here we have a mirror image relationship between half-life and decay. If you know the half-life or if you know the decay, then you simply use those numbers to divide the natural log of 2, and whatever thing you know can be used to figure out what you don't know. Now, some problems will just have you figure out the half-life or have you figure out the decay constant, but a lot of times you'll be asked to figure out how much is left. You will want to know what percent is left, or we'll want to know how many grams are left, or we'll want to know how many moles are left, or we might even want to know how many atoms are left. You start off with a certain amount, and then after a time it changes. Okay, so for that, we're going to have to use another equation. But please note, a lot of times you'll be given the half-life, but you'll need to figure out what the decay constant is in order to use the equations. The equations that come next don't usually show half-life. The equations that come next will usually have the decay constant. And you will have to convert the half-life into the decay constant by using one of these setups before you can use that equation. So this is a one-step problem, really. But the problems that come after this will be a two-step problem, and you're usually going to have to find K first. If K isn't given, you'll have to find it first. Now, again, I've been talking about mirror images. We've talked about how there's a mirror image between this function, e to the x, and this function, natural log. And I've talked about how there's two ways of measuring the rate of decay. One, we can talk about the half-life, and the other we can talk about the decay constant. And I've shown how we can use natural log of 2 to use any one of these to find the other. And again, they kind of mirror each other. Well, I'm going to give you another mirror now. I'm going to give you another symmetry, you might say, between these two relationships. So we're going to have two equations, and one of them is going to rely upon natural log of 2. And it looks like this. So this says the natural log of the concentration of some isotope at some time t equals the starting concentration, the natural log of the starting concentration at a time 0, plus the product of the decay constant and the time expressed as a negative number. So that is one equation, and we use this equation often we're trying to find the percent of something. And this uses the natural log on both sides. Then we have this other equation. It looks like this. And we often use this when, instead of a percentage, we're trying to find a given amount. We're trying to find, how much grams will be left, or how many atoms will be left, or how many moles will be left, right? So this is actually trying to find an amount instead of just a percentage. So this one goes like this. Now, this one and this one are kind of a symmetry because they're about the amount or the percentage of something at some time in the future, at some time. And this natural log a to sub 0 or n sub 0, these are both about what you started with. What was the starting amount, okay, at time 0. And this one adds negative kt as a term. And as you'll see, the natural log of a sub 0 will cancel out. And so that'll be very neat. But here, what we do is here, instead of using the natural log, we use e to the x, and we raise the power x to negative kt. So again, tt, 0, 0, kt. So again, these are two equations are similar, and they're very symmetrical. Now, of these two equations, which one's easier to use? I don't know. I think it depends on the person. I actually find the second equation easier to use. But you may like the first equation better. But I will tell you one thing for sure. The second equation is definitely the more useful one, because we'll use this one in a lot of different circumstances. In fact, a version of this equation is probably the most used equation on the planet, because while you can use this equation to figure out things like radioactive decay, you can figure out physical science things. This is also used in commerce. This is the same equation we use to calculate a home loan or a car loan or the rate of return on an investment after a certain time. We actually use this. And instead of this equation, in fact, can not only do exponential functions that might look like this, but they can do more realistic functions that have an S-shaped curve, where they change twice in the middle of the curve, which is more realistic, logistic curves. Okay, so we'll come back to that second equation, which is actually the more useful. What I'm going to do is I'm going to give you a problem. We're going to use this problem to figure out something. We're going to say that we have some element, and we're not going to even bother with what if the element is. We're just going to say, hey, how long, how long will it be if we know the half-life? How long will it be until we have, say, 40%? Okay, how long? And we're going to say that here the half-life, T1/2, we're going to say that half-life is going to be 5 years. Okay, so if the half-life is 5 years, how long is it going to take to get just to 40%? Well, 40% is what you'd have here at some time t. So we're going to take the natural log of 0.4, because that's the decimal version of 40%. Now, when we start this thing, we're not going to have 40%, we're going to have 100%. And the decimal that goes here for the amount at time 0, that's just going to be 1. I'll write 1.0. And then we're going to add negative kt. Now, you're going to like this. You're going to like this in some ways because it really is easier. First of all, let's go to a sub 0. A sub 0, we're just going to say that this is the natural log of 1. Well, this works out really nicely because you may remember if we have natural log of 1, that's just 0. So it turns out that when you do a problem like this, this will just cancel out. Now, we have the half-life, which is 5 years. We're not using the half-life in the problem, but we are using the decay constant, k. It'll be negative, but it's a decay constant. So before we can use this one, we need to figure out the half-life. So again, in this case, the half-life, T1/2, is going to equal natural log of 2 divided by 5 years. And that's just like the same thing as 0.693 divided by 5. A little calculator will come in handy here. So 0.693 divided by 5. And we're going to get this value. It's going to tell us that k it's going to tell us that k is 0.1386. Okay, so we needed k to do this problem. And just remember, k here is going to be 0.1386. Now what do? How do we go on? We're going to figure out the natural log of 0.4. To do that, we're just going to put 0.4 in the calculator and press the natural log key. Now notice that we get a negative number here. It tells us that it's a negative number. It's going to be negative 0.916. That's natural log of 4, and that has to equal negative KT. And K is this, and the time is what we're going to find. So negative KT's got to equal this, and this is K. Okay, so we're just going to rearrange this little sucker right now. Now, a big trick here is you got to remember that the K, you have to slap a negative sign on it. And that's going to be that number times T, right? This is negative K, this is T, and the whole thing's got to equal 0.0916. Well, what I want to do is I want to solve for T. So, of course, the way to do that is to divide both sides by negative 0.1386. Notice that when we do this, the two negative signs over here will cancel out. Now this just becomes math. And so 0.916 divided by 0.1386. We're going to determine that to get to 40%, we're going to have to go a little bit beyond 5 years, because 5 years would be 50%. And how long are we going to go? Turns out we go 6.6 years. That's the answer. So if you're asked to do a percent, you're going to use this formula, natural log of a sub t, the amount at some time t, equals the natural log of a sub 0 at time 0 plus negative kt. And if you set it up so that your starting amount is 100%, that just becomes 1. And then natural log of 1 is 0, so we just get rid of it. And so it's just going to be the natural log of whatever your decimal here will equal negative kt. If k isn't given, you have to use the half-life to figure out what k is from the half-life. And again, you would just take natural log of 2 divided by the half-life, and that gives you negative k. And then you divide both sides by whatever that is, and that will equal the time. And there it is. That's your answer. Now let's do the other equation. The other equation is n sub t. It's a number at some time t, and that's going to equal the original amount of substance at time 0, and we're going to multiply it by E sub x, and we're going to raise E sub x to the kt power. Now what this means, all this means is that when we say E sub x, x is the power we raised it to, and we're going to get x by taking the half-life k and multiplying it by the actual time that we want. So let's say that we have, let's use uranium-238. Uranium-238 has a half-life that's pretty big. It's going to be 4.9 times 10 to the 9th years. That's 4.9 billion years. It's a big number, okay? So that'll be T1 half. We're going to need K instead of T1 half. So let's go ahead and quickly figure out what K is from the half-life. Again, we're going to take the natural log of 2. So 2 natural log, get this number, 0.693 something, something, something. And we're going to divide it by this number, 4.9. We use the E key to enter the power. It's to the 9th power, so I put in 9. That's 4.9 billion, and now I do the math. And I get this tiny number. It says 1.41 to the negative 10. So in this equation, K will be 1.4 E negative 10. That's K. How did we get K? We took the half-life that was given and we used it to divide the natural log of 2. Okay, So there's our setting. Let's say that at time 0 that we started out with 16 grams of uranium-238. And let's say we're going to let this thing decay for 10 billion years. 10 billion years is going to be 1 e to the 10th years. So the question is, how many grams are we going to have left? If we start with 16, how many grams are we going to end up with if 10 billion years goes by? 1 times 10 to the 10th. Okay, so now we're going to solve our equation. NT we don't know yet, but we do know NO. We're going to start with 16 grams. And we're going to go E. We're going to raise E to a certain power, and that power is going to be the decay constant times the time. And remember, we're going to have to slap a negative sign on this. Our decay constant is 1.4 times 10 to the negative 10th. So I'll write that in parentheses. I'll write negative 1.4 times 10 to the negative 10th. Now this is tricky because again, it has to be a negative number, and since it's so small, it's a negative power. So we have to remember that it's going to be negative 1.4 times 10 to the negative 10th. We got a negative on both parts. And then the amount of time we're letting this go for a 10 billion years, which is 1 e to the 10th. Okay? So we're going to multiply these two numbers by each other, and that's what we're going to raise the power to. So first, let's do the hard one. 1.4. I'm going to slap a negative sign on it by using the plus minus key. Now I use the 2 capital E's, not lowercase, 2 capital E's to put in the power. It's a negative power, so after I put in 10, I got to flip the sign on that. Okay, so we got negative 1.4 to the negative 10 power. That's in there. Now we're going to multiply that by 1e10, which is the same as 10 billion. And lo and behold, we're going to get this number, which is just negative 1.4. So this becomes negative 1.4. But this is what we have to use our e to the x function. So we're going to literally raise e to the x to the negative 1.4 power. So we need to do that. Second function, e to the x, and there it is. When we take that number, negative 1.4, and we raise the constant e to that power, it becomes 0.246. I'll round it upwards because we got a 5 now. We'll call it 0.247. So this is now just 0.247 times 16. And that's going to tell us how much we're going to have in grams after 10 billion years. Okay, so again, we started off with 16 grams of uranium. This is our equation. We're told that we're going to let it run for 10 billion years, 1 times 10 to the 10th. We have to take the half-life and use that to find a k, and we did that. So we plug negative k in here times the time, which is 10 billion years. We get a number that when we raise e to the power, we get this, 0.247. Now we multiply it by 16. We get this, 3.94, blah, blah, blah. So after this amount of time, we would have 3.95 grams of uranium-238. Now here we're finding grams, but you could use the same technique for moles, the same technique for number of atoms. In general, we use the equation with the natural log of the amount and a concentration. We do that for a percentage, and we don't necessarily even need to know what the element is. But here, for anything else, where we're actually looking for a number in grams, moles, or atoms, we'll use this equation.